In the previous recording, I introduced you to the atom, the structure of the atom, and the particles, the three fundamental particles that make up the atom. Again, I expect that you knew most of it, but a couple of concepts that I wanted to make sure that you heard was that the of the three particles, the proton and the electron are the two that we're going to focus our attention on, and a crucial difference between these two particles is how different their masses are. They also, as I pointed out in the previous recording, the mass of the electron is almost 2,000 times smaller than the mass of the proton. And so I said near the end of the lecture that means if we exert a force on the proton and that same force on the electron, that the electron will achieve an acceleration nearly 2,000 times larger than that of the proton. And then I left hanging the question, what kind of force can we imagine applying on these incredibly tiny objects? So to help answer that question, I want to show you something here. So I've got a thing here. And actually I have three things. First thing I have is a plastic rod with a pointy end here. And I've got a piece of rabbit fur from an ex-rabbit. It was gotten from the rabbit, presumptively after the rabbit no longer needed it. That was funny. That was a joke. And yes. And the third thing I have is a random scrap of paper. Okay. And so here's what I want to show you, and I sure hope this works. All right, so there we are here. Okay, good. So what I'm going to do is, I don't know if I can do this. You can see both the stuff I want to show you and my face at the same time. Hello. So what I'm going to do here is, I'll be a little closer. You don't need to see my face. I'm not that interesting. But what I'm going to show you is, at least I hope so. Okay. So I'm going to tear little bits of paper off of this of various sizes. And by sizes, of course, I mean masses. So just a few more, because why not? Okay, that should be enough. Now, I'm going to take the plastic rod, which, yeah, there you are, and the rabbit fur. Now, this is a plastic rod. Not metal, plastic. And then this rabbit fur. And I do that, and then I bring the rod to the paper, and you can see what's happening. At least I hope you can. The paper is experiencing some sort of a force, and you know that there's a force because the scraps of paper here, their velocity right now is 0, and now their velocity is not 0. It wasn't a moment ago. There we go. You see? They're sticking to this plastic rod. Why in the world are they doing that? And how did they get it there in the first place? Well, that was cool. Yeah, they're actually jumping up into the air. Okay? And a thing that I particularly want you to notice, oh, it's got larger mass. The thing that I particularly want you to notice is that when this force happened, the plastic rod never physically touched the paper. This force happened over some distance. Okay, so the bits of paper experiencing this force without any physical contact between the paper and the plastic rod. Oh wait, I wasn't done. Because I want to show you something else. Kind of the same demonstration, except this time I have a metal rod. This is aluminum, as it happens. Pieces of paper back. The reason I'm doing this demonstration is because I suspect that most of you already know where I'm going with this, that I've got something I'm going to call electric charge. And electric charge, there's insulators and there's conductors, and you probably know these words, have heard of this. And plastic clearly is not Plastic is clearly not a conductor. Metal absolutely is a conductor. If you know what all that means that electric charge, what's electric charge? I'm going to tell you about that, but if you know, then you know. Electric charge moves through a conductor really easily, and it doesn't move through an insulator at all. And you'll notice that surprisingly perhaps, the metal rod has no effect, no force on this paper, whereas the metal has all the charge in the world. The plastic doesn't, or shouldn't, or it seems like it doesn't, and yet, big effect. All right, so a thing that I want you to get out of this is that absent any other knowledge, even if you have no idea what I was talking about when I was talking about charge and current and conduct moving and all of this stuff, the evidence is there was a force. The observation is that there was a force. And how do I know? Because the little bits of paper with their mass accelerated. They weren't moving, and then they were moving. They were clearly attracted to the plastic rod. They were just as clearly, by the way, not attracted to the metal rod, and we're going to have to explain all of this. But whatever, the crucial point that I want to get to is that there absolutely was a force on those pieces of paper. And our next task is to try to explain that force, describe that force, be able to calculate that force, be able to predict that force. Okay? Why? Because it's interesting. The universe is interesting. All right, so let's start thinking about that. Well, tempting as it is to go through with you in laborious detail the history of the discovery of all of this stuff, right now I'm just kind of doing a summary, so let me tell you what happened. A lot more experimentation of various kinds, similar to this, and doing all sorts of changing. Instead of pieces of paper, you're trying other things. You try pieces of metal, or instead of a metal rod, you try a glass rod. Instead of glass, you try other things. Instead of fur, you try silk, and various other combinations. Eventually, it was found that, yes, there's this force that can be exerted by one object on another object. It is true, as you saw, that force can exert itself without any physical interacting objects. And by the way, I don't want you to miss that. That is very, very unusual. Specifically, the fact that the force can happen without any physical contact between the objects. No, they're not. The objects never touch. And that's unusual. If you think back to all the other forces that you've heard about, there's the friction force. Well, that requires two surfaces in contact with each other. There's the tension force. That's a rope attached to some other object. Right? There's the spring force. A spring is attached to a mass. The only exception that we know to the requirement that in order for a force to exist, the two objects have to touch each other, the only exception to that is gravity. And now this one. So there's that. First of all, we have so-called action at a distance, force at a distance. The other discovery that was made is that the force that you just saw demonstrated there can actually either attract, as you saw the metal, the plastic rod attract the pieces of paper, but it turns out that under the right combination of objects, this new force can actually repel one object away from another rather than attract. So it can either pull or push, and the conceptual and physical model that was eventually constructed to explain all of this was to say that these two particles, the proton and the electron, carry another property along with their mass, another property that helps define what they are, and this new property was given the name electric charge, or just charge for short. We will discuss in days to come how the charge was measured and where this number came from, but for now, I will simply hand you the answer. Mass is a property that an object can have. A proton has a mass of 1.67265 times 10 to the minus 27 kilogram. A brick has a mass of about 1 kilogram. I have a mass of about 1 kilograms. All help define what the object is. Similarly, for charge, objects have a property that we call electric charge, and they have a certain amount, and the amount of charge that they carry helps define what kind of an object it is. In the case of a proton, the charge is given the symbol. There's actually two symbols that are often given to it, either Q sub E, which is the one I'm going to use, or sometimes just the letter E, and I'll explain the meaning of what the E is about in a moment. In any case, the charge is given the symbol Q sub E, and it turns out to be in SI units 1.602 times 10 to the minus 19th coulombs. A coulomb is, as I just said, the unit of electric charge in the SI system of units. Okay, it is named after a French-American physicist, Jean-Augustin de Coulomb. Back in the early 1800s, he did a lot of important work in studying electric charge, and so he got the unit named after him. Now, exactly what a coulomb is and how that works, again, that's coming. But for now, that's just the unit. I mean, where did kilogram come from, right? I mean, it's just something we chose. And so that's for the proton. For the likewise, it has an electric charge. And it turned out that the charge on the electron is exactly the same as the charge on the proton. 1.602 times 10 to the minus 19th coulombs, except I mentioned a little while ago that it was discovered that this new force we are, by the way, going to call the electric force, and this is to go along with the electric charge. This property that we call electric charge is the cause, the source of the electric force that one object can exert on another. In this case, the plastic rod exerted on the pieces of paper, that was an electric force. And the amount of charge that an object has is part of what goes into determining how big that force is. But what I wanted to say was, I remember I said a few minutes ago that electric force can either attract or repel. So push or pull. And so for reasons that will become clearer when I start doing equations and things, the best way to model that or to represent that fact that electric force can attract or repel is to give the charge on the proton and the charge on the electron opposite signs. Now, personally speaking, this is kind of a side note and editorial. I totally hate the choice that was made in which the charge that the proton carries from the electric charge that the electron carries. The idea here was to label the charge on the proton and the charge on the electron. And by the way, this is not a mistake that it's Q sub E for both. That's not a mistake. The goal behind labeling the charge on the proton versus the charge on the electron was to indicate that the forces that they cause point in opposite directions, exactly opposite directions, 180 degrees apart. This will be more clear in a minute. And so the labeling could have been any label that indicated oppositeness. We could have said that the proton has a charge of up and the electron down, or black and white, or in and out, or male and female, or whatever labels might have indicated oppositeness. Okay. Personally, I would have preferred black and white or something, but nobody asked me because for the small fact that I wasn't going to be born for 150 years until after this decision was taken. Anyway, so the choice was made to say that the proton carries a positive charge, the electron carries a negative charge. They carry the same amount of charge, but they are opposite in the sense that the force that an electron causes points in the opposite direction to the force that the proton causes, and therefore we label them in an opposite sense. There is a very great difficulty that creeps in when you try to actually do calculations involving these, and I will describe that difficulty when we start doing calculations. But I wanted to give you a heads up now that there is an issue that you have to watch out for. In any case, the bottom line is this electric charge is a physical property of the proton, a physical property of the electron, part of what defines a proton, part of what defines an electron, and the oppositeness is an indication of oppositeness of forces that they cause. It is for this reason, by the way, in the diagram in the first recording, when I was drawing a picture of an atom, when I drew the protons, I made them all little plus signs, and when I drew the electrons, I made them all little negative signs. So that was the reason for that. And in fact, we tend to use that same notation whenever we make a drawing of any kind that involves these charged particles. Okay? So if I wanted to make a diagram of what happened with the rod versus paper experiment, I might do something like this. So there goes my my rod there, and then here go bits of paper. Pen that you probably can't see real well here. In fact, I think that's so bad I think I'll get rid of it. Get close to this. Okay, and what happens is for reasons, well, do I want to explain this now? I'll hint at it now. I'll tell you what. I'll hint at it now. I'll give you a sort of a bird's eye view of the explanation of what happened, and then in later lectures we'll go into it in more detail. But here's the short version. In most objects, in most of the time, certainly the objects that you see around you, pretty much all the time, if you look around you right now, virtually every object that you see will have lots and lots of, well, let me start that over. Every object that you see around you, books, tables, chairs, cell phones, whatever you have, blankets, your roommate, they all have lots and lots and lots, and I mean lots and lots and lots of electrically charged particles. Lots of protons, lots of electrons. Each one of the protons, each one of the electrons in an object carries that amount of electric charge. Okay, in almost every object that you see around you, the number of protons and the number of electrons that the object has are equal. And so that means that as I said a few minutes ago, it is the existence of the electric charge property that of a proton and of an electron that is the source, or anyway the cause of this new force, this electric force that you saw. But I also said that the direction of the force that an electron causes is opposite the direction, always points the opposite direction of the force, the electric force that the proton causes. Well, that means that for any large object, if it carries just as much positive charge as it does negative charge, just as many protons as it does electrons, then for every attractive force, let's say, that an electron causes, there's a proton that will cause an equal and opposite repulsive force, and so overall, all of the forces end up canceling, and so the entire macroscopic object acts as if it has no charge at all. Well, it has lots of charge. What it doesn't have, though, is any excess or net charge, normally. Okay, so when we talk about an object that has no net charge, that doesn't mean there's no charge at all. It means it has just as much positive charge as it has negative charge. And so the overall effect is as if it didn't have any charge. But please understand, anytime I say that an object is uncharged or is electrically neutral, that's simply shorthand for saying it has lots of positive charge, it's got lots of negative charge, but it has the same amount of each. Until I do something actively to upset that balance, like, for example, rub that plastic rod with that rabbit fur. The effect of that was to, and why this happens, I'm not going to go into right now. I'm simply going to ask you to take my word for it. The effect was that the plastic rod picked up an excess of negative charges. Okay, so the ones I'm drawing are not all of the electrons that the plastic rod carries, simply the excess ones that I forced upon it by rubbing it with that wool skin, okay, that rabbit skin. And here's what happens. I said a little while ago that one of the effects, the effect of electric charges, is to create this new force. Okay, and through some mechanism that I have not yet explained, the presence of these excess negative charges here have some mysterious, I guess I should call it, electrical effect, or apply an electrical force on these pieces of paper. And what will turn out to be the case is that the negative charges in the plastic rod tend to attract the positive charges that exist on the paper. Now, I'm not saying the paper has excess positive charges, it doesn't, but it has some charges, and so these excess negatives will attract the positive charges that these pieces of paper have, and the force in this example happens to be attractive, and so the little bits of paper feel electric forces in different directions with different strengths. And of course, anything that feels a force, it accelerates in this case. And of course, they all accelerate in the direction of their forces. and so the pieces of paper jump up. And the next step is to describe and discuss the specific detailed nature of those forces. Okay. And in order to do that, at least successfully, there's a few more properties of electric charge that I need to explain, and we'll start that in the next recording.